Hi again. In this video, we are going to examine how external route information is passed between autonomous systems and how this external information is passed within these autonomous systems. The scale of routing on the internet is huge. Neither distance vector nor link state routing will work on a network the size of the internet. What is needed is a protocol that uses advertisements that include the path to better detect routing loops. The Border Gateway Protocol, BGP, was developed to provide that capability. The Border Gateway Protocol serves as a standardized routing protocol of the Internet. BGP exchanges routing and reachability information between autonomous systems. This protocol uses the BGP best path selection algorithm to sort through the different network routes and select the best path for each prefix in the routing tables. Recall from Chapter 4 that prefixes are the most significant bits in the IP address that represent the CIDR network address. There are two flavors of BGP. Exterior BGP, or eBGP, is used to advertise routes between neighboring autonomous systems. Interior BGP, iBGP, is used to propagate these learned external routes within an autonomous system. Note that the BGP protocol for eBGP and iBGP is basically the same, but is configured for different purposes. Let's examine this diagram. There are three autonomous systems shown: AS1, AS2, and AS3. All the ASs are running iBGP internally. The gateway routers are running both eBGP and iBGP. The gateway routers, 1C in AS1 and 2A in AS2, establish a peer relationship using eBGP. Similarly, gateway routers 2C in AS2 and 3A in AS3 also establish a peer relationship. The routers advertise paths to aggregate routes defined by destination prefixes. When a gateway router advertises a path, it promises that it will forward packets in that direction. The BGP protocol is classified as a path vector protocol. At its basic level, BGP selects the best path through the Internet by choosing a route that has to traverse the fewest number of autonomous systems. More completely, the protocol makes routing decisions based upon the shortest paths and other attributes such as network policies or rule sets configured by an administrator. Two of the most important attributes are the list of autonomous systems through which the prefix advertisement has passed, and next hop, which indicates the specific gateway router used to get to the next hop AS. Back to our diagram, we see an example of how policy affects the routing. Through eBGP, the AS3 gateway router 3D advertises a path to router X that is received by AS2 gateway router 2C. The ISP that operates AS2 has defined a policy that states that AS2 will accept the advertised paths from AS3. So, router 2C receives the AS3 advertisement for the path for router X and propagates that path via internal BGP to all the routers in AS2. There's another policy for AS2 that says AS2 will advertise this path to AS1. Thus, Gateway Router 2A sends this advertisement to its peer AS1, Gateway Router 1C, via eBGP. But what if a gateway router learns multiple paths to a destination? In our diagram, AS3 router 3A has now paired with AS1 router 1C in addition to AS2 router 2A. And AS1 policy determines router 1C's choice of the path, which in this case is the path AS3 to X. Router 1C propagates this path within AS1 via IBGP. BGP peers exchange BGP messages over TCP. BGP uses a variety of messages for communication between peers. There are 4 message types. The first is the open message. After a TCP connection is established between 2 BGP peers, they exchange BGP open messages to create and authenticate a BGP connection between them. Once the connection is established, the 2 systems can exchange BGP messages and data traffic. Once 2 routers have become BGP neighbors, they can start exchanging routing information via the update message. The update message advertises any feasible routes and can withdraw a previously advertised route. Keep alive messages are exchanged by BGP peers to determine whether a link or host has failed or is no longer available. BGP peers send notification messages when an error condition is detected. After the message is sent, the BGP session is ended and the TCP connection between the BGP systems are closed. For routing locally generated packets internally, an organization will typically run an interior gateway protocol such as OSPF. This diagram shows how the internal protocol and BGP work together to provide the correct route to the destination. The task here is to get packets from router 1D in AS1 to destination X. Gateway 1C in AS1 has learned the route to destination X from eBGP. This gateway router has propagated this information to all AS1 routers via IBGP. These AS1 routers know they must send packets to destination X via gateway router 1C. Through OSPF, AS1 router 1D determines the lowest cost path to router 1C is via its interface 1. In the next slide, the task is to get packets from router 1A in AS1 to destination X. As before, gateway 1C in AS1 has learned the route to destination X from eBGP. This gateway router has propagated this information to all AS1 routers via IBGP. These AS1 routers know that they must send packets to destination X via gateway router 1C. Again through OSPF, AS1 router 1A determines the lowest cost path to router 1C is now via its interface 2. When a router running BGP learns more than one route to its destination, the BGP protocol makes routing decisions based upon a particular attribute. There are 13 attributes that can be used to determine the route. The attributes are prioritized. The top priority is the local preference, which is set by local policy. The attribute next on priority is AS-path, which selects the shortest path to the destination. Third in priority is the next hop router, called hot potato routing. When the network traffic needs to lead from the autonomous system, sending the traffic to the closest exit is called hot potato routing. The closest exit point is the IGP's lowest cost path to exit the AS. ISPs, by default, perform hot potato routing for customer traffic. Let's look at how BGP can direct traffic by policy. In the diagram on this slide, ISP-A advertises the path AW to both ISP-B and ISP-C. However, for monetary reasons, ISP-B chooses not to advertise this route to ISP-C. So, if ISP-C receives traffic destined for W, ISP-C will route the traffic to W directly through ISP-A and not send the traffic via ISP-B. This policy can work in a slightly different way, as shown on this next slide. Customer Network X is dual home to both ISP-B and ISP-C. Since the ISP only wants to route traffic to and from its customer's network, and Customer X does not want to be a transit point between two ISPs, Customer X will not advertise to ISP how to get to ISP-C. Note that the dual home connection for X could provide traffic load balance or a failover in case of an ISP link going down. This split between inter-AS and intra-AS routing provides many advantages. Intra-AS routing is controlled by a single administration, hence policy is not usually concerned. Intra-AS routing policy has different goals. An AS administrator will want to control not only how that AS's traffic is routed, but also whether other AS's traffic is routed through its network. This policy may be driven by monetary, political, security, or performance reasons. As mentioned earlier, hierarchical routing dramatically reduces update traffic. It also significantly reduces the forwarding table space in the routers. This directly translates to the lower cost of the routers. An AS can focus on performance within its boundaries. Although performance is important in the inter-AS communications, policy may dominate the routing decision process. Next, we will look at SDN controllers in more detail.